Hello everyone. In this session, we have to start expression for displacement in SHM. Now in previous one we finished acceleration, we finished velocity, now displacement we have to start. So here displacement in linear SHM we have to start. Now we continue with the known thing. We know velocity is omega under root a square minus x square. So plus minus I am not written here, I consider the magnitude only. So I can write this velocity like this: dx by dt is equal to omega under root a square minus x square. Now we have to obtain displacement. So we can do one thing here. So I can transfer this square root to this side and dt to that side. So we get dx divided by this under root a square minus x square is equal to omega into dt. Now after that, we have to integrate this equation. So integrating both sides. So I am writing here, integrating both sides. So after integration of both sides, we get this type of equation: dx divided by root of a square minus x square is equal to omega integration of dt. Omega is constant, so integration of dt only. Now after that, but here, so this is standard integration, dx divided by this a square minus x square, and it is coming sine inverse of x by a, and integration of dt is t. Let me substitute these two values in above equation. Hence, this sine inverse of x by a is equal to omega integration of dt is t plus I write phi. Now what is phi? Phi is the constant of integration, where phi is constant of integration and it depends on the initial condition. Phi is the constant of integration and it depends on initial condition, means where the particle starts its oscillatory motion. Now after that we have to obtain displacement, means x we have to find out. So sine inverse we can shift to that side. Hence x by a is equal to sine inverse to that side is sine omega t plus phi. So we get this one. Now we have to obtain here x, so we can transfer this a to that side. So x is equal to a sine omega t plus phi, and this is expression for displacement in linear SHM. So this is displacement in linear SHM. Okay, I hope you understood how we get this displacement expression. Now here we have to write two cases for this. Now in the case number 1, we have to discuss, you know that at mean position displacement is 0, at extreme displacement is a, means plus a or minus a. But we have to consider here two cases when particles start from mean position. How much is the displacement? I told you here this constant depends on the initial condition. Initially, if particles start at mean, then how much is the phi at mean position, that we have to find out. Then we get the formula for displacement. Now see here, let us write two cases here. Case 1, when particle starts at mean position. When particle starts at mean position, it means that when t is equal to 0, time is 0. Time is 0 means in the initial stage, when time is 0, the particle is at its starting point. Starting point means what? It starts at mean. Particle is at mean position. When t is equal to 0, then x is equal to 0. Listen, when t is 0, that time x is 0 because particle is at mean position. Hence, I can write x is equal to a sine omega t plus phi, this formula. Now I substitute x is 0, a as it is, sine as it is, time is 0 plus this phi. Then I transfer a to this side, again 0. Then 0 is equal to sine of phi. Or I can write here phi is equal to, I can shift this sine to this side, sine inverse 0. Sine inverse 0. Now sine of which angle is coming 0? Sine 0 is 0. It means that hence phi is equal to 0. Means at mean position phi is equal to 0. Then I substitute phi 0. Hence displacement is x is equal to, in this formula of displacement I have to substitute phi is equal to 0. Then we get x is equal to a sine omega t plus 0 is omega t. And this is expression for displacement when particles start at mean position. I hope you understood this. Similarly, we have to write case 2 also when particles start at extreme. Now instead of writing separate thing, I will make some changes in this case number 1 because we don't have that much space to write below that. So I consider case number 2 here. I am making changes here in the case 1 only. When particles start at extreme, it means that when time is 0, particle is at extreme. When particle is at extreme, x is equal to a. So I can write x is equal to a. If x is a, then in that equation, instead of x, I have to write a. And this a as it is, sine as it is, t is 0. So 0 into this phi. Now this a is shifted to this side. This a is here multiplied to this side, a by a, 1. We get 1 is equal to sine phi. So phi is equal to sine inverse of 1. Sine of which angle is coming 1? You know that sine 90 is 1. So it means that phi is 90. So 90 degree. Or you can write phi is equal to pi by 2 radian. You can write pi by 2. You can write 90 also. Hence displacement is, in this expression of the displacement, we have to substitute phi is 90. So we get here x is equal to this a as it is, sine as it is, omega t as it is. Instead of phi I write 90 or pi by 2. Anything you can write. Sine of omega t plus pi by 2. Sine of any angle plus 90 is coming cos. So we get x is equal to a cos omega t. And this is expression for displacement when particles start its oscillatory motion at extreme position. I hope everyone understood how we get this. Now here we learn displacement in linear SHM. In that expression, in general, displacement equation is x is equal to a sine omega t plus phi. But if you have idea about the initial position, if particles start at mean, then displacement is x is equal to a sine omega t. And if particles start at extreme, then displacement is a cos omega t. Or some more points you can remember. At mean, the phase is 0. 0 degree, 0 radian, anything you can write. At extreme, the phase is pi by 2 radian or 90 degree. So here also, the phase is pi by 2 radian. So that's it in this today's session. We continue this chapter in the next lecture. Thank you.